Assalamualaikum warahmatullahi wabarakatuh. Greeting to all of us. Good afternoon, ladies and gentlemen. Let me introduce myself. My name is Ade Riyawan. I am doctoral student in Department of Statistics IPB University, Bogor, Indonesia. On this occasion, I would like to present our paper entitled Robustness of Extreme Gradient Boosting, Regression 3. I will perform my presentation into 5 parts: introduction and problem, algorithm, method, simulation studies, and conclusion. Introduction. The use of machine learning spreads across all aspects and becoming very important in many areas. Two crucial factors drive this successful application is the effectiveness of a statistical model that capture the complex data dependencies and scalable learning system that learn the model of interest from large dataset. In 1996, Raymond used pegging as procedure to make estimation in order to increase accuracy. This introduced the randomness into function estimation procedure that could improve their performance. Early implementation of ABS, introduced by Freud and Shapiro in 1996. They use weight to the observation. This was considered an approximation to deterministic weighting when the implementation of the baseline didn't support observation weight. And then recently, Bremen in 1999 used hybrid pegging boosting, or called adaptive pegging. It replaced the baseline in regular boosting procedure with the corresponding peg baseline and substitute out of peg residual for the ordinary residual at each boosting step. Motivated by Bremen, a minor modification was made to gradient boosting to incorporate randomness as an integral part of the procedure. Specifically, a subsample of the training data is drawn at random without replacement from the complete training data set at each iteration. Friedman 2002. At randomness in gradient boosting by take n per n data each iteration called stochastic gradient boosting. And the last improvement, Chen and Questrin 2016 developed algorithm for scalable boosting trees called extreme gradient boosting. So what is the problem from all of the machine learning method? We also have a big question about the robustness of the use of the method. So this paper will focus on the study of robustness of the use of extreme gradient boosting. What is the algorithm of stochastic gradient tree boost? The main of the key of the algorithm is there is a parameter called subsample that take n per n data for each iteration. We look on the algorithm, they take the random permutation from 1 to n from the data set and make it of the subsample from each iteration. The method we use here is simulation study for the regression tree, which we will create the simulation data from the regression. Robustness of extreme gradient boosting will depend on the particular problem at hand. In addition to gauge robustness of regression model, is necessary to evaluate its performance over many different simulation situations. This research adopted then modified the simulation by Friedman 2002 and general data sets according to this regression equation. And we will create the data set based on this regression equation with the error normal have the mean 1 and sigma equal to 1. Each data set create for n equal to 500 and 5000, and we will divide into 90% as data training and 10% as data testing. We will create 4 data set with 5% outlier, 10%, 15%, and 20%. So all of data set we will use atau application the XGBoost and the least square model to the dataset. Result and discussion. Here we can see the box plot of the applied XGBoost gradient boosting on the dataset with 5% outlier, 10% outlier, 15% outlier, and 20% outlier. We can see that the use of gradient boosting very depend on the learning width parameter we use. We apply the XGBoost with the different learning rate from 0.3 and 0.1, 0.05, and 0.025. We can see that at each box plot here, we know that the use of learning width will also have impact in the prediction accuracy. We can see that the use of the smaller learning width will create the most best accuracy. It's seen from the more small RMSA. And for the outlier with the bigger presentation of outlier, for example, for the 20% outlier, will also have the more bigger RMSA compared to the smallest outlier. The addition of outlier will interfere with the model, as seen from the increasing RMSA. For example, in a data set of 500, we see that the RMSA median value for an outlier 5% is lower than that of 10%, 15%, and 20%. The same RMSA distribution pattern also occur in 5,000 dataset. In this table, we can see the RMSA value for its different learning rate and outlier percentage. We can see that the smaller the learning rate value will be give the smaller of the RMSA. The results are the same for the 500 and 5,000. The learning rate affect improving the estimation of the response variable. Meanwhile, when we view from the percentage of outlier, we can see that the larger of the outlier so will give the RMSA value more increase. In other words, the greater percentage of outlier will cause the estimation of the response variable to be less robust. The second table, we can see that the use of subsample here, we use the 0.75 and 0.5 from the dataset. The subsample value means the processing is only carried out on a portion of dataset in each iteration. For example, the subsample 0.75, meaning that the data process is only 75% of the total dataset. This table compare the RMSA value from the 75% and 50% subsample with the similar neck and burning value, which are the more data is processed in each iteration. The rule of each option is to form a model. Bigger the subsample, the smaller of error value. However, this can have an impact on curve of overfitting. Here we see in the graph of the RMSA for the comparison of XGBoost and the least square model. We see that the dash is the XGBoost and the line is the least square model. We see that the RMSA built from a linear model is the higher than the XGBoost. It's occur on the 500 dataset and also on the 5000 dataset. So what is the conclusion of our study here? The XGBoost as one of many machine learning methods has good performance on prediction model, but we still have the question about the robustness of regression model that vary depend on the data set being handled. Here we study focus on the data containing outlier that we found that the key performance of XGBoost gradient boosting is depend on the selection of learning rate and subsample. Learning rate has a big influence in determining prediction accuracy. Smaller learning rate will give better prediction. Subsample describe the use of data at each iteration. More data to be processed will give more biased prediction. XGBoost with the proper parameter selection will be more robust than the linear regression or least square model in the context of outlier treatment. Of course, we still have many questions about the XGBoost and about the robustness of the machine learning. I give the future research challenge here. The first is the application on real dataset. Of course, we have many questions. How XGBoost will perform the prediction in the real data challenge. And the second is robustness on classification tree. Here I have an evaluate from the classification tree because here I only focus on the regression tree. And the third challenging research is the how far missing value can be handled by XGBoost. We know that XGBoost have a lot of advantage in handle missing value, but we didn't know how far XGBoost can handle the missing value. And the last, the study of parameter setting on nested dataset. We know that dataset sometimes we cluster the data into the subgroup, and we have many questions about the performance of the machine learning, such as XGBoost on the cluster data or nested dataset. And of course, still many other future research challenge that we can study for more interesting research. Here, that is all of my presentation from our research. Thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.